complex topics into the essential insights you need. Today, we're diving into, well, one of the biggest puzzles in physics. Trying to connect general relativity of the universe on the grand scale with quantum mechanics, the bizarre rules of the ultra-small, and right at the heart of quantum weirdness is this idea of wave-particle duality. We're going to explore how string theory, a really revolutionary concept, tries to make sense of it all. We're drawing from excerpts of The Resonant Universe, string theory, and quantum duality. Our aim here is to pull out the key ideas so you can really grasp this.
Right. The mission for you listening is to get a handle on how the basic building blocks of everything act like waves sometimes, particles other times. It really depends on how you look. And then we'll see how string theory comes in, suggesting maybe everything's made of tiny vibrating strings. It's a whole new picture of reality.
Okay, let's unpack this then. Let's start with the core quantum idea itself, this duality. So wave-particle duality, it sounds completely counterintuitive. What experiments actually show this happening?
Well, it's fundamental. Things like electrons, photons. They just don't behave like simple billiard balls or simple waves. They kind of switch personalities depending on the experiment. It's really the central mystery quantum mechanics has to explain. It forces us to rethink what reality even means at that level.
And this is where I think the double-slit experiment comes in. That's always presented as the classic example, the real head-scratcher.
Oh, absolutely. Feynman famously said it holds the heart of quantum mechanics. Because think classically. Fire particles, like tiny bullets, through two slits. You expect two lines on the detector screen behind.
Makes sense.
Thin waves, like waterways. You get that characteristic interference pattern, peaks and troughs where they overlap. Thomas Young showed light does this back in 1801, so light's a wave, right?
Seemed settled for a while.
Until the 20th century. Experiments by folks like Davisson-Germer showed electrons, things we think of as definite particles, also create an interference pattern.
Like electrons acting like waves.
Exactly. And it gets weirder. If you send them through one by one, so they can't possibly be interfering with each other, they still build up that wave pattern over time.
One at a time. How?
It's like each electron somehow goes through both slits and interferes with itself. A solo interference act, you could say. It's bizarre.
Okay, that is genuinely mind-bending. What about this observer effect we always hear about? How does simply watching change things? And is it really about watching?
Yeah. That's a crucial point, and often misunderstood. If you put detectors right at the slits to see which slit the electron actually goes through, poof, the interference pattern vanishes.
It disappears.
Completely. You just get the two simple bands, like you'd expect for particles. But, and this is key, it's not about a conscious mind observing. It's about the physical interaction of the detector. To get that which path information, the detector has to interact with the electron, and that interaction disrupts the delicate quantum state.
So any interaction that reveals the path destroys the wave behavior.
Precisely. It highlights Niels Bohr's principle of complementarity. The wave-like behavior, interference, and the particle-like behavior, which path information, are mutually exclusive. You can see one or the other, but never both at the same time. And it's not like the electron decides to be a wave or particle. Before you measure, it exists in a superposition. Think of it as a wave of probability, exploring all possibilities.
A wave of possibilities.
Yeah. The interference pattern shows where those possibilities constructively and destructively interfere. Measurement forces one possibility to become real, collapsing that wave function, and you see a localized particle hit. Duality isn't the electron being confused. It's about how measurement interacts with its quantum nature.
Okay, so beyond the double slit, what are some other key examples? How else did we figure out light acts like a particle and matter like a wave?
Good question. For light acting like a particle, the photoelectric effect was huge. Einstein explained it in 1905. Shine light on metal, the electrons pop out. But the energy of those electrons depends on the light's color, frequency, not how bright it is. Dim blue light worked better than intense red light.
Why is that?
Einstein's insight was that light energy comes in chunks packets called photons. Each photon has energy E, h being Planck's constant. Only a photon with enough energy, high enough F, could knock an electron loose. That screamed particle. Compton's scattering later showed photons also carry momentum, reinforcing the particle picture.
Okay, so light can be a particle. What about matter being a wave?
That was Louis de Broglie's brilliant idea in 1924. He thought, well, if waves can act like particles, maybe particles act like waves. He proposed everything has a wavelength. Lambda equals h divided by momentum.
Everything, like this desk, me.
Technically, yes. But Planck's constant h is incredibly tiny, like 10 to the minus 34. So for everyday objects, the wavelength is astronomically small, completely undetectable.
Okay.
But for tiny things like electrons, with very small momentum, the wavelength becomes significant enough to be measured, which is exactly what Davisson and Germer confirmed. It showed this duality is universal. Planck's constant is the key bridge here. It links the particle aspect, energy, momentum, quantum, to the wave aspect, frequency, wavelength, probability.
So with all this strangeness, how do physicists actually write this down? What's the mathematical tool?
That tool is the wave function, usually written as psi, that Greek letter. It's the central thing in quantum mechanics. It mathematically encodes everything knowable about a quantum system state.
Is it a physical wave, though, like water?
No, not really. That's a common misconception. It's more abstract. It's a complex mathematical function. It involves imaginary numbers whose square gives you the probability of finding the particle somewhere.
The square of its magnitude. The Born rule.
Exactly, the Born rule. Stu tells you the probability density. You can only predict probabilities, not definite outcomes, before a measurement. And how this wave function changes over time is described by the Schrödinger equation. Because it's mathematically a wave equation, solutions naturally show superposition and interference.
So back to the double slit.
The electron's wave function literally goes through both slits, interferes with itself, and creates that probability pattern on the screen. When the electron hits the screen measurement, the wave function collapses, and we see a dot. So really, wave-particle duality is kind of a limitation of our classical language. The fundamental thing is this quantum object described by its wave function. It behaves consistently according to quantum rules. It just looks weird from our classical perspective.
So that really clarifies the quantum foundation. Okay, now let's bring in string theory. How does this very different idea connect to quantum reality? What's its core proposal?
Right. String theory makes a really bold claim. It says, forget point particles. At the most fundamental level, the building blocks of reality are tiny, one-dimensional vibrating loops or strands of energy strings.
Not points, but lines. How tiny are we talking?
Unimaginably tiny. The Planck length, around 10 to the minus 35 meters. If you blew up an atom to the size of the known universe, a string would be about the size of a tree. So, yeah, way beyond anything we can see directly.
Wow. Okay, so shifting from a point to a line, that sounds like a fundamental change. How does that affect how things interact?
It changes everything about interactions. A in-particle moving through time traces a line, a world line. Where world lines meet, you get sharp interaction points, vertices. That's the picture in standard quantum field theory.
Okay.
But a string, being one-dimensional, sweeps out a two-dimensional surface as it moves through space-time, a world sheet, like a ribbon.
A world sheet.
Yeah. And when strings interact, say two strings join or one splits, their world sheets merge smoothly. There are no sharp points, no vertices. It's more like smooth plumbing connections.
And why is that smoothing important?
It's crucial. Those sharp points in quantum field theory lead to mathematical nightmares calculations that blow up to infinity, especially when you try to include gravity. It breaks the theory. String theory, smooth world sheets naturally avoid these infinities. This smearing out of the interaction makes it mathematically consistent, particularly as a quantum theory of gravity. It's a direct result of strings being extended objects, not points.
Okay, so if everything's made of strings, how do we get all the different particles we see? Electrons, photons, quarks. Are they different types of strings?
That's the really elegant part.
Yeah.
No, they're not fundamentally different types of strings. They are all, in theory, the same fundamental string, just vibrating in different ways.
Like notes on a guitar string.
Exactly like that. It's a perfect analogy. A string vibrating in one pattern, one note, appears to us as an electron, vibrated differently. It looks like a photon. Another pattern, a quark. The entire blue of particles is just different vibrational modes, different harmonics of this one underlying entity.
So particle properties come from the vibration.
Precisely. The energy of the vibration determines the particle's mass. More energy, more mass, by EMC2. Think of that as the volume or pitch. The specific mode or pattern of vibration determines things like electric charge and what forces feels, and that's like the timbre, the quality of the note.
And other properties. Spin.
Spin comes from the rotational state of the string, and whether it's an open string with ends or a closed loop also matters. Open strings are often linked to matter particles and forces like electromagnetism, while closed loops naturally give rise to gravity. You can even have strings winding around extra dimensions if they exist, which adds other quantum numbers.
It sounds incredibly unified. All particles, all forces, just different tunes played on the same string.
That's the promise, yes. Compare it to the standard model, where you have matter particles, quarks, leptons, and force carriers, photons, gluons, as separate categories. In string theory, they all emerge from the same source, string vibrations. And crucially, gravity isn't just tacked on, it's required. One specific vibration mode of a closed string loop automatically, inevitably, has the exact properties needed for the quantum particle of gravity. Massless, spin 2. It just pops out of the math.
So unification isn't the goal, it's a result.
It's an emergent property. The theory naturally unifies everything because at the deepest level, there's only one kind of thing, the string. The differences we see are just low-energy consequences of how those strings vibrate and interact.
This is a truly beautiful picture. So how does it handle the wave-particle duality we started with? Does string theory get rid of it?
No, not at all. String theory is a quantum theory. It fully incorporates quantum mechanics, including superposition, uncertainty, and duality. It just applies them to the string itself. What it does is give us a richer understanding of waviness. There are actually two kinds of waves involved with the string.
Two kinds. Okay, what are they?
There's the internal physical vibration of the string, like the guitar string analogy, and then there's the external quantum probability wave for the string as a whole object moving through space.
Let's unpack that. What does it mean to quantize the string's internal vibration?
Right. Quantization is applying quantum rules. A classical string could vibrate with any amount of energy, but quantum mechanics says energy comes in discrete packets or quanta. So when you quantize the string's vibrations, you find they behave like quantum harmonic oscillators. Their energy levels can only take on specific discrete values. It's like the rungs on a ladder, not a smooth ramp.
And that connects to particles how?
Through EMC2 again. Those discrete energy levels of vibration translate directly into a discrete set of possible masses for the particles the string represents. Each allowed vibration mode is a particle type with a specific mass. So the particleness, the fact that we see distinct particles like electrons and muons with fixed masses, comes directly from quantizing the string's internal waveness, its vibration.
Okay, that's the internal wave. What about the string as a whole object? Does it behave like a quantum wave, like the electron in the double-slit?
Yes, absolutely. That's the second, deeper layer of waviness. Because it's a quantum theory, the string itself, the whole entity, is governed by the uncertainty principle. It doesn't have a perfectly defined position and momentum simultaneously. So just like an electron, the string as a whole must be described by a wave function. But because a string isn't a point, but an extended loop or line, its state is described by something much more complex, a wave functional.
A wave functional sounds complicated.
It is. It's like a wave function, but instead of assigning a probability amplitude to each point in space, it assigns an amplitude to every possible shape and configuration the string could take in spacetime. It's a function whose input is itself a function describing the string shape.
Wow, okay.
But this wave functional is the true quantum wave for the string. It spreads out, it interferes. If you could do a double-slit experiment with strings, this wave functional would pass through both slits, interfere, and create a probability pattern for detecting the entire string configuration.
So the string itself exhibits duality.
Exactly. The particle aspect is when you measure it, and the wave functional collapses to a specific string shape at a specific location. The wave aspect is the interference pattern built up from the superposition of all possible string paths and shapes described by the wave functional. String theory takes duality to a whole new level.
Okay, let's try to nail this down. Two kinds of waviness. Can you summarize them clearly?
Sure. First, internal wave, vibration. This is the physical oscillation of the string. Think frequency, harmonics. Quantizing this gives discrete energy levels, which determine the intrinsic properties of the particle it represents. Mass, charge, spin. This gives structure to the point particle.
Got it. Internal vibration defines the particle type.
Second, external wave, wave functional. This is the quantum probability wave describing the string as a whole object moving and interacting in spacetime. It governs its dynamic behavior where it might be found, how it diffracts and interferes. This is the standard quantum waviness applied to the string.
Okay, internal wave defines what it is. External wave defines how it behaves.
That's a great way to put it. String theory wraps both concepts together. An electron is a string vibrating in the electron mode, internal wave, and its probability of being found somewhere is governed by its wave, functional, external wave.
It's a really cohesive picture. Stepping back then, what are the bigger implications of this for the universe, beyond just particles?
Oh, the implications are vast. It potentially reshapes our understanding of space-time itself, the laws of physics, even how we do science.
One of the most famous, or maybe infamous, predictions is extra dimensions, right?
That's right. It's not something put in by hand. It actually falls out of the mathematics needed for the theory to be consistent. Early versions needed 26 dimensions, but the more favored superstring theories require 10 spacetime dimensions. M-theory hints at 11.
10 or 11. But we only see 4, 3 space one time. Where are the others?
The idea is compactification. The extra dimensions are curled up incredibly tightly into tiny complex shapes at every point in our familiar space. Think of a garden hose. From far away it looks like a 1D line, but up close you see it has a 2D surface, including the small circular dimension around its circumference.
So these extra dimensions are like that tiny circle, but much smaller and more complicated.
Exactly. Often visualized as complex geometric objects called Calabi-Yau manifolds. They're curled up down at the Planck scale, far too small for us to perceive directly.
Why does the shape of these hidden dimensions matter?
This is crucial. The geometry of these hidden dimensions dictates the physics we see. How strings can vibrate depends on the shape of the space they're vibrating in. So the specific way these dimensions are curled up determines the allowed string vibrations, which in turn determines the masses and charges of all the particles, the strengths of the forces, basically the fundamental constants of nature.
So the laws of physics could be determined by geometry.
That's the incredible prospect. If we knew the exact shape of the compactified dimensions, we could, in principle, calculate things like the mass of the electron or the strength of gravity from first principles. It would move physics from describing what to explaining why.
How does string theory mesh with quantum field theory, QFT, which is the basis of the Standard Model and works so well? Are they competitors?
Not really competitors. QFT is seen as a highly successful, low-energy effective theory. It's what string theory looks like at the energies we can currently access, where we can't resolve the tiny strings, and particles appear as point-like excitations in quantum fields.
So QFT is an approximation.
A very, very good approximation in its domain. But string theory provides more fundamental underpinning. Remember the infinities in QFT, especially for gravity.